Okay, I have 2 pieces of paper and 2 pieces of aluminum foil. I'm going to sandwich the foil between the paper. Now, I could just use 1 piece of paper, except for what I'm about to do. If I smooth this paper out and flatten it down, I'll have 2 plates. Each plate being one of the pieces of aluminum foil, separated by the thickness of the paper, if I can manage to get those things flattened down real well. Now what I'm really going to do is I'm going to take these plates and I'm going to curl them up. Take another piece of paper here. And then I'm going to take a cylinder, a piece of PVC plastic, and I'm going to roll the system up. Now the 2 pieces of paper, or the 2 pieces of foil, are completely separated by the paper. I'm just slipping the cylinder off, okay? So we see there's a piece of foil on the inside, and it wraps around with 1 piece of paper, and then the other piece of foil wraps around with the other, and it comes toward the outside. And if I can get a set of leads onto the inside piece of paper, or piece of foil, and onto the other, then I've just rolled up a parallel plate capacitor. Now there's more that we can do, and we'll talk about that a little bit. But that's essentially the idea of how a lot of capacitors are made. Now, a lot of capacitors now are solid-state ceramic, and I'm not completely sure exactly how they're manufactured. They're solid-state devices of one kind, but they have the same properties as a parallel plate capacitor. And the parallel plate capacitor is easy to understand and very instructive. So, if we have a parallel plate capacitor of this type, let's say with an area of, well, let's say we have a 30 centimeter by 50 centimeter piece of foil, and another one, excuse me, and we wrap those up in a piece of paper, or just leave them flat. Doesn't really matter, as long as we get them close together. Then we're going to have an area of 1,500 square centimeters. If we use paper 0.01 centimeters thick, then we'll have a separation of 0.01 centimeters. And from this we can calculate the capacitance from this information. Now let's just do a numerical analysis, or a numerical calculation here. Let's say we have a charge of 10 to the negative 8th coulombs on the capacitor. Okay, just so we can have some numbers to grab onto, then we'll symbolize the process. Okay, we see that our charge density sigma is then 10 to the negative 8th coulombs divided by 0.15 square meters. The 50 by 30 centimeters is 1,500 square centimeters, or 0.15 square meters. And now that comes out 6.7 times 10 to the negative 7 coulombs per square meter. And that'll be our sigma. Now what's our electric field? Well, without going through all the details of Gauss's law and everything, it's 4 pi k sigma. And if we calculate that using the 4 pi k, we get about 7.4 times 10 to the 4th newtons per coulomb. It could be off by a tenth or so. I did these calculations mentally. You should always verify the calculations. Sometimes they're way off, but usually they're fairly close. Okay, the voltage across the capacitor is the product of the electric field and the separation. In this case, that's 7.4 times 10 to the 4th newtons per coulomb multiplied by the 0.01 centimeter separation, which gives us 7.4 newton meters per coulomb. 0.01 centimeters is 10 to the negative 4th meters multiplied by the 10 to the 4th newtons per coulomb. Here it'll give us a result in newton meters per coulomb, or joules per coulomb, or volts. So this tells us that a 10 to the negative 8th coulomb charge on a capacitor of this size, formed in this manner, should have a charge, if the charge is 10 to the negative 8th coulombs, the voltage would be 7.4 volts, something we could actually accomplish with the handheld generator. Not that we'd be able to use it for anything, we wouldn't even be able to detect it. as we'll see in a minute. Okay, so the 4 pi k, well, voltage is E times D. We go through the symbolic calculation, the 4 pi k Q over AD. If we just did this calculation using the charge and the area and the separation, we would attain 7.4 volts. Now, to find the capacitance, to do the numerical calculation, we divide the charge 10 to the negative 8th coulombs by the 7.4 volts, and we get 1.4 times 10 to the negative 9th coulombs per volt, or 1.4 times 10 to the negative 9th farads. That's the same thing we would have gotten if we had just substituted the area and the separation into the formula, the Q over D that we obtained by simply doing this analysis. So if we put, okay, the point here is we just need the area and the separation. We didn't really need a charge. Everything that we did with the charge in the numerical calculation ends up canceling out at the end, and we don't have to be specific about the charge. If we just know the area and the separation, that is sufficient to give us the capacitance. But doing this numerical calculation again reminds us of everything that's going on in this situation. Now we'll point out also that this is a very tiny capacitor, 1.4 billionths of a farad. The capacitors that we use with the lab kits, which are smaller, are about half a farad and a farad. They're huge capacitances. The disadvantage of these capacitors, incidentally, is that they're very slow. They're very slow to discharge, so they're not really practical for a lot of applications.